Okay, so in this simulation, we saw the parent nucleus, that was polonium-211, and as these nucleons move around randomly, eventually it'll be able to shoot off a particle, an alpha particle, and we see from the key that that alpha particle is made of two neutrons and two protons. Now, because two protons were lost, this transmutates polonium into a completely different element, lead. So from the simulation, you should have seen that an alpha particle is a particle that's made up of two protons and two neutrons. That alpha particle can be written as 2,4 alpha or 2,4 helium, where the 2 is the number of protons. And remember, 4 is not the number of neutrons. 4 is the number of total nucleons. So since there's 2 protons and 2 neutrons, that's 4 nucleons. And you can write it in either way. Now, this is a highly charged particle. That means it strongly interacts with matter. With this 2 plus, because it's taking away 2 protons from the nucleus, that makes the parent nucleus negatively charged. When we write out decay equations, however, feel free to drop this charge on the top right-hand side. Feel free to drop that so we're not like trying to keep track of too many things at once. To backtrack for a second, an alpha particle is ejected when there are too many nucleons in the nucleus. Think about why this might be. There's too many nucleons in the nucleus and it has to get rid of some of them, right? In this case, 2 protons and 2 neutrons makes a super stable chunk to shoot out. Remember with the whole even number stability thing? That would be a super stable particle. So an alpha particle is very stable on its own, and that's why it usually doesn't shoot out something like 2 neutrons and 1 proton. There's a reason it's 4 nucleons total. It's also a heavy massed particle. Its mass is 4 AMU, 4 atomic mass units. It's a heavy, highly charged particle that strongly interacts with matter. I want you to think of the alpha particle as like the bull in the china shop when it comes to particles. It's big, it's heavy, it hits everything. And when do alpha particles happen? This chart you're not going to have to use in particular, but nuclear physicists use it all the time. Think of it as like the periodic table of the elements plus. It's the periodic table of the elements with every single isotope that can exist of a specific element. Roughly the same number of protons and neutrons. Then those nuclei are stable. That's right over here. Roughly the same number of protons and neutrons. We get special extra bars of stability along those magic numbers of 8, 20, 28, 50, 82, and 126. But alpha particles are these yellow nuclei over here. They tend to occur where there's either too many protons, which you can see because that's where the number of protons is largest, either where there's too many protons or too many nuclei in general. Notice that everything past about this point over here, everything past lead, is inherently unstable. There is no way to make a roentgen atom stable in any configuration of its nucleons. Alpha particles are emitted when the nuclei is just too big and it's trying to eject particles as quickly as possible to reach stability. So now I'm going to introduce how to write this in a decay equation. So we start with this unstable parent nucleus. In this case, it's uranium. Uranium has 92 protons and 238 total nucleons. Well, because that has just too many nucleons, uranium emits an alpha particle, which I can either write as 4,2 helium or 4,2 alpha, and that's totally fine either way. And notice that I dropped the 2 plus on the top right so that we're not dealing with too many superscripts at a time. Now, notice that 92 is equal to 90 plus 2. This more stable daughter nucleus then no longer has 92 protons, so that means it changed element. It is not uranium anymore. Like in this case, you really can turn lead into gold, but it would take a nuclear reaction to do so. Right? This is called transmutation. Transmutation is when some sort of decay causes one element to completely change to another. That one element changes to a different element as a result of this nuclear reaction. So let's take a closer look for a second. Please notice that the mass number is conserved. You can think of this as kind of a statement of conservation of matter, conservation of mass, that is. It's conservation of mass because if I have 238 approximately AMUs of mass to start, I have 238 nucleons, and 4 of them were ejected, I should have 234 left over. Similarly, the number of protons is conserved. You can think of this as like conservation of charge. So if there are 92 protons to start and 2 get ejected, well, there's 90 left over, and that element is thorium. Those two nuclear decay properties, the conservation of mass and conservation of charge, that works for every reaction, not just alpha particles. Notice that in this super important uranium decay, a neutron plus uranium turns into a barium, krypton, and 3 neutrons. This is actually the fission chain reaction in a nuclear reactor. So notice that 1 plus 235 is 236, and 141 plus 92 plus 3 would also equal 236. So the mass number is conserved. On the bottom, 0 plus 92 is equal to 56 plus 36. So proton number is conserved and charge is conserved. So how would you do this yourself then? Let's say I give you a parent nucleus of polonium-218. It emits an alpha particle because it just has too many nucleons. It's like, psh, alpha particle, gone. I would be able to use conservation of mass to see that there must be 214 nucleons in the daughter particle, in the daughter nucleus. Oh, and by the way, sometimes you'll hear people read that as daughter nucleus or progeny nucleus. Similarly, by conservation of charge, if there's 84 protons to start and 2 are ejected, there are 82 protons left over, and it has to transmutate from some element to a different element. Element number 82 on this mini periodic table here is Pb. Not peanut butter, lead. Because, you know, that makes sense for naming. Pb, lead. I think it has something to do with a Greek or Latin root word. Finally, before you go and try this yourself, I want you to know that this alpha decay doesn't necessarily only happen once. Sometimes it happens over and over and over until your unstable nucleus finally reaches a stable state. We call this a decay chain. So in my examples, you've seen me do polonium to lead. It actually starts all the way up here, kind of off screen here, with uranium. Uranium decays into thorium, into radium, into thorium again, into radium again, into radon and polonium over and over and over, all the way until it reaches lead, a stable nucleus at last. So we'll be doing one decay at a time, alpha decay. Try this out on your own. Best of luck.